Welcome to the next project, Arduino and C Programming. We will be using Tinkercad to complete our projects. Are low power, affordable and easy to interface devices that are used to measure short distances. This project is about how to use the ultrasonic sensor with Arduino Uno to make distance measurements. So what is ultrasound? Ultrasound is a high-pitched sound wave whose frequency exceeds the audible range of human hearing. Humans can hear sound waves that vibrate in the range of about 20 Hz to 20 kHz. However, ultrasound has a frequency of more than 20 kHz and is therefore inaudible to humans. So how do ultrasonic sensors work? Ultrasonic distance sensor actually consists of two ultrasonic transducers. One acts as a transmitter that converts the electrical signals generated by Arduino into 40 kHz ultrasonic sound pulses. The other acts as a receiver and listens for the reflected ultrasonic sound pulses. When the receiver receives these reflected ultrasonic sound pulses, it produces an output pulse whose width is proportional to the distance of the object that reflected the ultrasonic sound pulses. This pulse width can be measured to find out the distance. They detect the distance of the closest object in front of the sensor. They are capable of measuring distances from 3 centimeters up to 400 centimeters. Commonly available ultrasonic sensors work on 5 volt, so it can be connected directly to an Arduino or any other 5 volt logic microcontroller. What electrical signal is generated by Arduino? The ultrasonic sensors usually have a trigger pin and an echo pin. The trigger pin receives the electrical signals generated by Arduino. The echo pin generates a pulse whose width is proportional to the distance of the object. In some sensors, the trigger and echo pin are the same. The trigger pin is set high for around 10 microseconds. After that, it is pulled down to low. This is the signal expected by the sensor at the trigger pin. On receiving this, the sensor transmits an ultrasonic burst of 8 pulses at 40 kHz. Meanwhile, the echo pin goes high to initiate the echo back signal. If there is an object within the range of the sensor, then these pulses are reflected back. The echo pin goes low as soon as the reflected signal is received. This generates a pulse on the echo pin. The width of the pulse can vary from 150 microseconds to 25 milliseconds depending on the time taken to receive the signal. If there is no object, then the pulses are not reflected back. In such a scenario, the echo signal times out and goes low after 38 milliseconds. Thus, a pulse of 38 milliseconds indicates that there is no object in the range of the sensor. So how to calculate the distance? The width of the received pulse is used to calculate the distance from the reflected object. We know that distance is equal to speed into time. The speed of sound is 340 meters per second. Suppose we received a pulse width of 500 microsecond width, then distance can be calculated as shown here. That will give the answer as 17 centimeter. But the duration of the pulse indicates the time it takes for the signal to be sent and reflected back. So to get the distance, you have to divide your result by 2. So the distance is 8.5 centimeter. So this is the theory behind the project. Now let's see the block diagram of the project. Our intention here is to measure the distance of an object using the ultrasonic sensor and then display the distance measured on a 16:2 LCD. So we need an Arduino Uno board, an ultrasonic sensor and a 16:2 LCD display module. The Arduino Uno does the computation of distance measurement and displays it on the LCD. The block diagram shows this idea. Now let's move on to the schematic. We already saw how a 16:2 LCD is connected to an Arduino board. So we apply what we learned in earlier sessions and connect the LCD as required to the Arduino. The ultrasonic sensor we use here only has 3 pins, the VCC, the ground and the signal pin. We connect the signal pin to digital pin 7 of the Arduino. It's time to develop the flowchart. We saw how the ultrasonic sensor works. Triggering the ultrasonic sensor and measuring the received signal pulse width manually is a lot of work. However, there are many libraries available for this purpose. One of the popular libraries is the NewPing library. If you use a real hardware, then Arduino IDE requires this library to be installed. This library is not included in the Arduino IDE, so you will need to install it first. To install the library, navigate to Sketch, include libraries, manage libraries, search for the NewPing library, and then select and install. If you are using Tinkercad, then this is not required. We will be using Tinkercad here. So the flowchart we develop will be for its use, but you can certainly adapt it and use it for Arduino IDE. So first, we initialize the 16 by 2 LCD and display a banner message on LCD, that is measured distance. We wait for 3 seconds after that. Next, we invoke the read ultrasonic distance routine and measures the distance. Next, we display this distance on the LCD screen at the second row. This process continues indefinitely. So this is how the setup function and loop function works. Now let's look at the internals of read ultrasonic distance function. The trigger pin and echo pin are the same here. So when we use it as a trigger pin, we have to set it as output pin first. Then we clear the trigger pin by pulling it low for about 2 microseconds. We then set high to the trigger pin for about 10 microseconds. After that, we pull it low again. Next, we have to use the pin as echo pin, so we set it as input. Then we read the pulse duration using the pulse in library function. This duration is returned by the function. So this is how the basic flowchart looks like. Next, we develop the firmware in accordance with the flowchart. First, let's write the code for the LCD. As we had seen earlier, we include the header file for LCD and then call the LCD function to initialize the library with the pin numbers. In the setup function, we initialize the LCD and display the banner message. Next, we write the read ultrasonic distance function for interfacing the ultrasonic sensor. We follow exactly what was explained in the flowchart. That is, we set the trigger pin as output, we clear it first for 2 microseconds, then we set it high for 10 microseconds, then we clear it again. We then set the echo pin as input and read the pulse duration using pulse in routine. The duration is returned. In the loop function, this duration is converted to centimeters and then basic data manipulation is done to get it displayed on the LCD. On running the simulation, the LCD display shows the messages. On clicking the sensor, a range where the sensor works is displayed. You can move a small object within that range. The sensor measures the distance of the object and displays it on the LCD if the object is within the range. Outside the range, the sensor fails to measure the distance. To scroll data on the screen, first we set the row positions as required. For scrolling data from left to right, we will change the column index. It can vary from negative value to values up to 15. In effect, we are changing the cursor position as needed. One important thing in scrolling is that we have to delete the previous data from the screen using the clear function each time before updating the screen with new data. So this is the theory behind text scrolling on LCD screen. Shown here is the block diagram of the project. The LCD is connected to the Arduino. In addition to that, we have also connected the Arduino to the PC. This is because the parameters for text scrolling, such as the text to be scrolled, the direction to be used, the row to be used, all these parameters are received from the PC to Arduino. These are the requirements of this project. The UART communication protocol for transferring these details to the Arduino has to be developed, which we will see shortly. Now let's see the schematic. There are no surprises here, it's what we have already seen. Here we connect the LCD with the Arduino. Now let's create a flowchart. So first we initialize the 16:2 LCD and display a banner message on LCD. We then receive the commands transmitted from the PC over the UART. There are 5 commands to be received. The first command to be received is the start command. Only after the start message has been received, other commands can be received. Then each command is received and the parameters are extracted. The row enable command is received. The scroll direction command is received. The text to be scrolled is also received. All these commands are received and the parameters are extracted. Then finally, the end message is also received from the PC over UART. Once the end message is received, the execution moves to the scrolling section. The text is scrolled according to the parameters passed from PC to Arduino. To keep the discussion simple and compact, the flowchart given is a very minimal one. It can be extended even further. We haven't included any error detection schemes in the design. For example, what happens if a specific command has not arrived? How long the Arduino should wait for the next command? What should be done if an invalid value is received from the PC? All these could be included and the project will become complex. For the sake of a simple and compact discussion, we have avoided those details. But you can do that as an assignment and also, if possible, include more features and improve upon your design as well as coding skills. Now let's move on to develop the firmware. First, let's develop the protocol for UART communication. Arduino waits for certain messages from the PC. The messages have a specific structure. Arduino waits until the start message is received. Arduino stops receiving messages when the end message has been received. Based on the messages received between the start and end messages, the configuration details are updated. Once this process is completed, Arduino proceeds to the task of text scrolling. Let's take a closer look at the messages. Each message will have a header and a footer. The footer is the hash character. The header varies based on the message type. The LCD has two rows, so text could be scrolled on both rows in either direction, that is left to right or right to left. The user is given choices to enable or disable text scrolling on both rows. For example, to enable the text scrolling on row 1, use the message *ENA*1 hash. For row 2, the message is *ENA*2 hash. To disable the scrolling, *ENA*0 hash could be used. Similarly, to set the scroll direction, use *dir*0 hash for left to right and *dir*1 hash for right to left. The text to be scrolled is supplied by the message with the header *txt*. Hope this clears the doubts on the message structure. Now let's move on to complete the firmware according to the flowchart and the protocol we just developed. As usual, we include the header file of the LCD and initialize the LCD library with the pin numbers. In the setup function, we initialize the LCD and serial routine and print a banner message. We then create a few variables to store the configuration parameters received from the PC, which includes the row enable or disable parameter, the direction of the scroll, and the text to be scrolled. We also create an array of the commands to be received from the PC and a few other supporting variables. We will see its use later. In the setup function, we write the code to receive the parameters from PC. We put this code in an infinite loop. The execution exits this loop only when the end command is received. The first command to be received is the start message. We write the code to receive each command and extract the configuration parameter from it. Once the end message is received, we exit the loop and execution passes on to the loop function. In the loop function, the scrolling of the text is done. The cursor position is changed according to the scroll direction and the row number. Let's run the simulation and see the working. A set of sample commands are given in the code itself as comments. You may use them. A servo motor is a closed-loop system that can control its motion and final position using a position feedback system present in it. This ability to precisely control the position of its shaft is its main feature. Servos can usually rotate 180 degrees. Typically, servos expect a control signal of frequency 50 Hz to position the shaft at a target position. The width of the pulse determines the angular position of the servo. Suppose you send the control voltage for a target position to the servo motor. The position sensor captures the actual position and sends it back to the error detector where it is compared with the target position. The error detector corrects the actual position of the motor to match with the target position. There are 4 main components inside a servo motor, such as a DC motor, a gearbox, a position sensor, and a control circuit. The position sensor rotates when the motor rotates. This position sensor generates a voltage that is proportional to the absolute angle of the output shaft. This voltage is compared to the control voltage given to the signal line for achieving a target position. The error detector corrects the position until the 2 signals reach a difference of 0. Generally, pulses with 1 millisecond duration correspond to 0 degrees position. 1.5 millisecond duration pulse refers to 90 degrees and 2 milliseconds refers to 180 degrees. Though sometimes this can vary with different brands. The main consideration when choosing a servo motor is its torque, its operating voltage, the current it draws, and its size. Small-sized hobby servo motors could be connected to Arduinos directly, but it is always recommended to use a separate power supply for them. Now let's see the schematic. Here's a typical circuit diagram of connecting an Arduino with a servo motor. The servo motors have 3 wires: power, ground, and signal. We simply need to connect the signal pin of the servo to any digital pin of the Arduino board. Connect the ground and the positive wires to the external 5-volt power supply. And also connect the Arduino ground to the servo ground. Since this is a demonstration, we power it directly from the 5-volt Arduino pin. Servos can draw quite significant amount of current when they are at load. This can result in the resetting of Arduino board and also jittery motion. So if you are using real hardware, it's recommended to use a capacitor across the ground and the 5-volt pin. It will act as a decoupling capacitor which will provide additional current to the system at startup when the DC motor starts. We shall use the Arduino servo library to control the servos. First, we shall see how a servo motor is interfaced using this library in Tinkercad. Include the header file for servo library first. Then create an object of the servo class. In the setup function, we attach the servos to the library by providing the pin numbers and the maximum and minimum pulse durations. Here we attach the servo connected to pin 9. This function has certain significance because when you are using real hardware, if you find that the servo motor doesn't cover the entire range of 0 to 180 degrees, then the minimum and maximum values of pulse duration in the attach function has to be adjusted for fine-tuning the range of the servo. In the loop function, we move the servo by specifying the angle in the right function. Minimum angle is 0 degree, maximum angle is 180 degree. On running the simulation, you can see the servo motors rotating. connect three servos to Arduino. Here pin numbers 9, 10 and 11 are used for connecting the signal pin. We also wire a potentiometer to the A0 pin. Our requirement is to rotate the servos when the potentiometer is rotated. Now let's create a flowchart. The methodology is very simple. First, we create the objects for the three servos connected. We then initialize the servo library using the attach function for all the three servos. In the main loop, the potentiometer value is read using analog read function. The read value is mapped to the range of servo library. This is then used to control the servo using the write function. So that's it. That's the flowchart. Now let's move on to develop the firmware. Now that we have understood the usage of the servo library, let's implement the firmware of our project according to the flowchart. So we just have to create objects from the servo class for each servo motor and attach it to the corresponding Arduino pin in the setup function. In the loop function, we read the potentiometer value using the analog read pin. The value returned is in the range of 0 to 1023. But the servo write function requires values in the range of 0 to 180 degree. So using the map function, we scale the values returned by analog read to the range of servo library. After that, we apply the values. We wait for a delay of around 15 milliseconds for the servo to complete the action. On running the simulation, we can adjust the servo motor position by rotating the potentiometer. There is an Arduino board, an LCD, a 4x4 keypad, a red LED, a green LED, and a servo motor indicating the movement of the door lock. When the system is switched on, the user is presented with a screen to enter the password. The red LED is switched on, indicating the door is locked. The password is fixed as a 4-digit password. On entering the correct password via the keypad, access is granted, the green LED is switched on, red LED is switched off, and the servo motor is turned 90 degrees. The buzzer beeps each time a key is pressed. It beeps 3 times when the door entry access is given. Pressing the key A anytime during the password entry process aborts the process and clears the screen. The user can start entering the password from the beginning. After the door is unlocked, the door returns back to the locked state after a certain delay. Now let's see the schematic. The LCD connections are exactly the same as we had seen earlier. The rest of the connections are to be done as shown here. The servo is connected to pin 9. Red LED is connected to pin 10. Green LED is connected to pin 13. The buzzer is connected to pin 8. The row pins of the keypad is connected to A0, A1, A2 and A3, whereas the column pins are connected to pin A4, A5, A6 and A7. Now let's create the flowchart. We have already explained the working of the system. Now let's draw the flowchart to achieve that. First, we initialize the LCD as 16:2 display. Next, we attach the servo library with the servo motor connected to pin 9. We set the angle as 0. We initialize the buzzer pin 8 and the LED pins 10 and 13 as output. We switch on the red LED and switch off the green LED. We then display the welcome screen on LCD asking the user to enter the password. In the loop function, we read the key press. We compare the key pressed with the next character in the password. If it doesn't match, we ignore that particular key press. If it matches the character, then the key press is acknowledged by a beep sound. Also, the key press count is incremented. If the key A is pressed, the entire process is aborted and starts again. Otherwise, when the key press count reaches 4, the password match is complete and the door is unlocked. The actions in response to password match includes message display, switch on green LED, switch off red LED, turn the servo 90 degrees. After a specified delay, the door returns back to the lock state and the welcome screen is shown on LCD. The red LED becomes on and the green LED becomes off. Now let's move on to develop the firmware. As usual, we include the header files of keypad, LCD and servo first. We then initialize the LCD library with the LCD pin connections. We follow the same procedures we had done for the keypad interfacing here also. We define the number of rows and columns. We also create a map of the keys and define the pins to which the rows and columns are connected. We then initialize the keypad library. We also define the pins to which the buzzer and the LEDs are connected. We then declare a variable for storing the key press count and the position of the cursor. In the setup function, we do exactly as it was explained in the flowchart. First, we initialize the LCD as 16:2 display. Next, we attach the servo library with the servo motor connected to pin 9. We set the angle as 0. We initialize the buzzer pin 8 and the LED pins 10 and 13 as output. We switch on the red LED and switch off the green LED. We then display the welcome screen on LCD asking the user to enter the password. We create a separate function for the welcome screen display. In the loop function, we read the key press. We compare the key pressed with the next character in the password. If it doesn't match, we ignore that particular key press. If it matches the character, then the key press is acknowledged by a beep sound. Also, the key press count is incremented. If the key A is pressed, the entire process is aborted and starts again. Otherwise, when the key press count reaches 4, the password match is complete and the door is unlocked. The actions in response to password match includes message display, switch on green LED, switch off red LED, turn the servo 90 degrees. After a specified delay, the door returns back to the lock state and the welcome screen is shown on LCD. The red LED becomes on and the green LED becomes off. Let's run the simulation and see the working.